In this video, I'm gonna cover the very basics of an LC circuit. So what's an LC circuit? LC circuit. Well, an LC circuit is a circuit made by a capacitor and an inductor. Now, if I just have to draw it, I will draw it like this. A capacitor and then an inductor connected together. This is my C and this is my L. Now, what happens? Well, let's suppose that, if they're both discharged, so the capacitor is discharged and the inductor is discharged, then nothing happens. There is no current flowing through it whatsoever. So, and that's not funny because, you're just staring at that, nothing happens. So let's suppose that the capacitor is going to be charged. If the capacitor is charged, because, I don't know, perhaps you are touched with a switch, like a power supply, and with direct current, and it charged the capacitor. So if the capacitor is charged, we're going to have positive on this side, charge on this side, and negative charges on this side that actually wanna go one to the other. So since they wanna go one to the other, and they can't actually go through the capacitor, they're just gonna go through the circuit. Now, since the inductor is discharged initially, this is the condition we assumed. So capacitor charge and inductor discharge. The charges are going to flow through the circuit and go to the inductor, which is essentially going to act like a resistance, but it's going to store this energy in terms of a magnetic field, which I'm going to call B. So those two are the charges inside the capacitor, which are then going to be transferred and flow through here, and we're going to have a magnetic field inside the inductor. But then the capacitor is going to be discharged, so the inductor is going to see a change in the magnetic field caused by the flow of current, and since nature hates change, it's going to try to fix that. It's going to try to induce a new current to keep everything as it was. So a new current is going to flow and it's going to go to the capacitor, and its capacitor is going to be charged. But in doing that, the inductor is going to be discharged and the cycle continues. So the capacitor effectively charges the inductor and the inductor charges the capacitor. So since we assume that those, we are in an ideal world, so those wires don't have any kind of resistance, then this cycle is going to continue to go on over and over again. So it's going to go on forever. So if we were to plot this in a graph where I have the time here and QV here, I will have something that looks like this. Why sinusoid? Well, because the current is not actually, I actually said that it was going to go on over and over again, but essentially the current flows in this direction, and then in this direction, and then in this direction, because one charges the other, and it changes direction every time that these things go on, and so every cycle. So we will get essentially a sinusoid. But what if we are in the real world and thus this circuit does have a resistance? So it will be like putting a resistance here somewhere in this schematic, or as I said, we can think about being in the real world, and so having this wire with a certain resistance. Well, then our pretty sinusoid is is gonna become flat, like something that looks like this, until it becomes flat and there is no current whatsoever. We can also think about this as the movement of a pendulum. So we know that the relationship between the charge Q is Q equals CV. But as I said, right now I wanted to focus on a thing, which is the pendulum. If we think about this motion as a pendulum, which is initially in this position, and then it goes here and down, so it gets to this position, and then it goes to this position, and so on. So it goes here, and then it goes back here and back here, because it's all oscillating. Okay, then the pendulum is eventually gonna stop. And if you think about the path of the pendulum as a plot in the axis, in the xy axis, but as a vector field, then you will have the motion of the pendulum going to zero in an exponential decay. So let's suppose that this is my initial velocity. Well, then my vector field, my pendulum, the path of the pendulum will be to zero in an exponential decay, like so. Now, does this remind you of something? Well, let's see. Let's write a few relationships here. We can think about this energy here as the potential energy of this pendulum, and then it's gonna use this potential energy till it's gonna be attenuated, and then it's gonna be totally dissipated till it gets here. It's attenuated by many things like the viscosity of the air and so on, but it's not important, of course, the gravity and so on, but it's not important right now. This is just to tell you about the kind of spiral that those are gonna get into in the real world, or if we had the resistance here. But in the real world, as I said, we have resistance in the cable. Now, let's write a few relationships, shall we? Now, the relationship will be that Vrms of the capacitor will be equal to Vrms of the inductor. But then I can also say that the IRMS times the impedance of the capacitor will be equal to the IRMS of the impedance of the inductor. What's the impedance of a capacitor and what's the impedance of an inductor? Well, the impedance is essentially how this opposes the change. So basically the current in this case. So the impedance of a capacitor will actually be 1 over omega c, and the impedance of an inductor will be omega L. Now, we can actually get rid of those IRMS and say that the impedance of C is equal to the impedance of L. And then XC becomes equal to XL. And I can substitute those two and say, okay, therefore we have that 1 over omega C is equal to omega L. So 1 over LC is equal to omega squared. But then 1 over the square root of LC is equal to omega. Now, if I were to plot something like this and put, for the sake of this schematic, let's put something like a resistor here. Well, not like this, but like this. Okay, it's gonna be by resistor R. If I'm gonna put a resistor, and therefore this becomes more realistic. Okay, if I put there in a resistor, and essentially this becomes flat and this is an exponential decay, then I would have that XR. What's the impedance of a resistor? Just the resistor itself, because in the resistor we have that both voltage and current are in phase, so the impedance of the resistor is just resistor itself. But then real impedance, Z, well, real is a term used loosely. I mean, the impedance itself, Z, will be R squared plus XL minus XC squared. And if we were to plot this in a graph, let me see if I can squeeze it here with omega. We will basically have that, well, first of all, the resistance R will be a certain fixed value. I'm going to put it here. Then XC will be something like, well, exaggerated, something like this. Ooh, my poor R. What happened to my poor R? So XC will be 1 over omega C. And then my XL will be omega L, like so. And finally, my Z, my impedance, will be something that, well, and this one will be actually my something like here, I think. My omega resonance. This is gonna reach the resonance frequency. So my impedance will be something like this. So this is my Z. So yeah, it's pretty much what happens when people talk about an LC circuit. Cheers and bye.